Hi everyone, Joe here, back at it for another lab. Today it's Lab 3, Planetary Science, and I wanted to go through briefly, just introduce to you the lab, and then go through each part with you. Part 1 is going to be looking at specifically angular diameter and distance. How big something looks in the sky is part of it, both how big it actually is and how far it is away from us. Part 2 in the lab is going to explore terrestrial planets, which are the rocky planets, versus Jovian planets, which is our gas giants and ice giant planets. Part 3, we're going to look at temperature and how temperature really is a measure of molecular motion. How fast the molecules are moving and how much energy they impart is part of the temperature equation. And then we're going to look at the Coriolis effect, the actual spin of objects that pass over a rotating surface. Of course, our planets are rotating, our winds are blowing over the surface, they're going to curve, and so we're going to talk all about the Coriolis effect in part 2 of the lab today. Part 4 of the lab today. Part 5 of the lab continues to look at the Coriolis effect. We're going to do a little demonstration with that. Part 6, magnetic fields, and we'll actually look at how a magnet works and how the Earth's magnetic field works like a bar magnet. Part 7, we're going to be discussing and looking at interiors of planets and how the interior of a planet can actually generate a magnetic field. So lots of great stuff for you today. Planetary Science Lab starts now. Okay, part 1, we're going to look at the diameter of objects, and how big they are is a direct result of how big they actually are and how far away they are from us. This is called angular diameter because your eye, a single point, stretches out and can mark the side, one side and the other side of a thing, and it kind of makes an angle. And that angle is what we're going to measure, and that angle, that angular diameter actually is related to distance and actual diameter. So your lab today, part 1, you can see that there, part 1 with the diameter of objects, goes through and describes all that. I encourage you to read this about how the diameters of the different planets look from the same magnification. Also then we're going to look at the using your hands in order to tell how big something is in the sky. Your hand extended at arm's length can give different angular diameter measures. And then we have the actual mathematical equation that we're going to be working with there, the relationship there, and the information below. So let me show you how this works. All right, so here we are from a view outside of my classroom, and you can see that there's nice trees, fence, a garage over there in the distance, and a nice garbage bin over here. I'm going to extend my arm out away from my body, and you can see my hand here from our vantage point. You can see that my hand is about 10 degrees of arc wide, and if I was to stick out my index finger, it would be about 1 degree of arc wide. So if I'm going to measure objects and kind of give an estimate of how big are things in the sky, or how big the angular diameter is, I might use my finger. So if I'm going to see how high this fence post is, for example, I would see that if I extend my index finger at arm's length, it's about 2 index fingers tall. And then further, if I was like, for example, to look at that garage back there, see the garage door, I would say that that's about 1.5. We'll go with 2. Let's move it back here. From my eye, we'll go with 2 index fingers wide. Okay, so if my index finger is 1 degree of arc wide extended at arm's length, then the garage is about 2 index fingers wide, and the fence post here is about 2 index fingers tall. We're going to use that information then to help us construct a scenario where we can actually calculate our distance from here in my window to that fence post and all the way over to that garage. All right, I'm coming to you at the desk of Mr. Shane here. And I wanted to finish helping you work through part 1. I want you to know first off that I went ahead and I crossed out height of trash can nearest sidewalk, height of sign that reads B1200 wing, and height of trash can at the intersection down the road. Cross all 3 of those out. The particular lab I'm working from today is not at Kish, and it doesn't have those. So I just wanted you to be able to use what we have available to us, and that is the fence post height, which we just looked at, the distance between two fence posts, and the garage. And again, for each of these, what we're going to do is find the angular diameter, which is how wide does it appear to our eye. And we're using our hand extended at arm's length. I use my index finger. You can use your pinky as well to get 1 degree. For our purposes here, the fence post height was 2 degrees, okay, or 2 index fingers. I went ahead and measured in between the posts, and it is about 3 fingers, and the garage was about 2 fingers wide. So our angular diameter for each was 2 degrees, 3 degrees, and 2 degrees of arc. The other part is the actual diameter, and I went out and measured the height of the fence post, and it's 1.75 meters. The width between 2 fence posts is 3 meters, and the width of the garage, yeah, it was kind of weird. When I went over and measured some random person's garage, but I snuck in and snuck out and got a 5-meter measure for that. So we're going to explore this relationship between angular diameter and distance using our mathematical relationship. And the mathematical relationship then is the actual diameter is equal to 2 times pi times the distance away from the object, so how far you are away here, times the angular diameter divided by 360. And we can rearrange that equation for little d, because that's what we need to find. We have a and we have d, but we need to find little d. So rearranging that equation, bringing the a and the 2 pi into the bottom and the 360 up to the top, leaving d on the other side, we have d equals 360 times big D over 2 pi a. So this is the equation rearranged so we can use it. If I'm calculating how far I am away from, my eye was away from that fence post in our window, what I'm going to do is go ahead and take my distance and put d there, is equal to 360 times the actual diameter, and I measured that to be 1.75 meters. Okay. Whoops. And doing a little piece of paper here, it's buckling on me. And then we've got 2 times pi, and then times a, which is the angular diameter, which we measured was 2 degrees using our fingers. And again, this is an estimate. So if you go through and do this calculation, you're able to come up with the actual distance. And you're going to get the distance in meters. So I have my trusty calculator here, trusty ancient calculator. 360 times 1.75. I get that answer is 630. I'm going to divide that answer by 2 because we have 2 down here. I get 315. I can divide 315 by pi, so I'm going to divide that by 3.14. That's 100, and then divide it again by 2, and my answer comes out to be about 50 meters away from the fence post. So from the window, when we were looking down the window, it was about 50 meters. We can do the same calculation for the others, okay? Finding out how far we are away from the fence post, we should get about 50 meters again if we calculate this out, and indeed we do. We should get a different distance to the garage. The garage was way far off in the distance. We should expect this to be in the hundreds of meters away from us. So I'm going to encourage you to use this equation and plug in the different a and the different d to get the answer for distance here. And we should get around, like I said, 50 meters here, thereabouts. And then we should get in the hundreds of meters here. And of course, if you calculate the distance of Mars, if you're looking at the actual diameter of Mars being 6,800 kilometers wide, and our angular diameter of Mars is way small in the sky. It's 0.00708 degrees wide in our sky. Obviously very small, right? So we're going to use that number and this number in the same equation to calculate how far we are away from Mars. All right, so going to give you some time to work on that, finish up part 1, and we'll move on to part 2. Okay, part 2 of the lab is looking at terrestrial versus Jovian. The 4 terrestrial planets closest to the Sun, Mercury, Venus, Earth, and Mars, are the terrestrial planets. They're Earth-like, they're rocky, they're relatively high in density, made of silicate rock with an iron-nickel core. Whereas the 4 Jovian planets, the ones beyond Mars, Jupiter, Saturn, Uranus, Neptune, those are Jupiter-like, mostly liquid, a lot of ice in some of them, thick atmospheres, overall densities that are around water. So I'm going to turn you loose on this part, and you can do part 2 on your own by reading these and looking at these diagrams to decide whether or not the characteristic that's listed is either a terrestrial characteristic or a Jovian characteristic. And you'll put T for terrestrial or J for Jovian here. So go ahead and finish part 2 and come back to me for part 3. All right, part 3 of our lab is looking at how planetary atmospheres and the molecules in them move. And really, a measure of molecular motion, that's called temperature. It's the average kinetic motion of the molecules in a material. So things like the sun and the planet's interior cause the temperature, the quote-unquote temperature, to change. And what is temperature? Well, it's really just a measure of molecular motion. What I have in front of you is a beaker full of cold water. And I just got this water out of the refrigerator here, and I put the thermometer in for us to measure. And it looks like the temperature here is about 7 degrees C, or about 40 or something, about 55 degrees Fahrenheit. So we're going to use cold water for this demo. And we're going to record that temperature in our lab under the cold water beaker temperature. So we're going to go ahead and use 7 degrees C. And so go ahead and write that in next to the cold water beaker temperature for part 3. And what we're going to do is we're going to time how long it takes for the food coloring to disperse through this liquid. Now you can see I have a stopwatch here. I'm going to use that here to demonstrate how fast this food coloring moves through. So hopefully we'll be able to see exactly, oh boy, I'm fumbly here. We'll be able to see how this all pans out. So we're going to look for the food coloring to disperse pretty evenly through the liquid. So here we go. Oh boy. Source of error there, my stopwatch. was pretty touchy. Now that's pretty cool, right? To watch the food coloring disperse through the water. Note that it's sunk way down and now it's kind of splashing back up and moving around, but it's really in drizzles. It's not really kind of dispersing out amongst the rest of the water. It's kind of more in fumes here. It's taking it a while to reach around. And as we watch, the clock keeps ticking. And we're kind of looking for dispersion throughout the entire liquid. Judging a little bit, it's a little bit hard to judge when that is, but we'll keep our clock running here. And the food coloring is starting to make its way down and through the liquid. Still just ribbons of food coloring, not really dispersing amongst the liquid. When you have a cold atmosphere, the molecules aren't moving very fast, and so things don't disperse very well through that because the molecules aren't moving very fast. Cold temperatures equals slow moving molecules. That would be what you would see in a Jovian planet, for example, with a cold atmosphere. We're going to go ahead and stop it right here, even though it's still struggling to disperse through. We're getting close to dispersion here. Still pockets of clear water, but we'll go ahead and stop the stopwatch, I guess, right about now. and we got about 1 minute and 56 seconds. So under dispersion time, next to cold water beaker, you're going to want to write 1 minute and 56 seconds. All right, we're going to do the same thing, except we're going to make this water hot. All right, so here we give me a second here to replace the cold water with hot water. All right, here we are with our hot water beaker, 200 milliliters of hot water, and I've got the thermometer in there. I'm going to pull it out really quick and measure the temperature quickly because the temperature goes down very rapidly. I can see right here that the temperature is about 119 degrees Fahrenheit, or about 47 degrees Celsius. So you take my word for it. You can see here we are, boom, there. Look at how fast it's going down. It was at 47 degrees C. Now it's all the way down to 42 degrees C and so forth. So in the temperature for hot water, write 47 degrees C. The cold water temperature was 7 degrees C, but we're going to write 47 degrees C for the hot water beaker. And we're going to go ahead and bring in our red food coloring here, and we're going to bring in our trusty stopwatch. Okay, and let's go ahead and drop in some hot water, drop some food coloring in hot water, and see how fast it disperses. So here we go. All right, we see similar ribbons of color as we did before. Really cool looking, right? But look at how much faster that's dispersing. If you go back and look at the cold water dispersion, it was much slower. But this, because the molecules in the water are moving faster, they're bumping against one another faster, it's causing the food coloring to disperse quicker. In a warmer atmosphere of a planet, the molecules in that atmosphere are moving faster, and you're going to have, therefore, a warmer temperature. So now we're pretty close to dispersed here already. If you compare where we're at now with where we were at with the cold water, we're pretty close to dispersed. I'm going to go ahead and hit that at 51 seconds. So for warm water dispersion time, we can go ahead and write 51 seconds. Whereas the cold water dispersion time was 1 minute 56. This is more like just under a minute. All right, so we'll go ahead on to part 4 after this. Okay, the lab part 4 deals with the Coriolis effect. And you see this section here, it gives a description of how atmospheric circulation takes place, how the air rises in the warm areas and sinks in the cold areas, and when the planet spins, it deflects the winds and causes them to curve and swirl. So the part here is to actually spin a chair and have the piece of paper in the chair and have a marker going out as you spin. Now, it's very difficult to do, but I'll show you the general idea. If I was to take my pencil or my pen here and go put it right here in the middle and go draw slowly outward as I spun the chair around, like so, okay? As I spun the chair around, I would draw a line outward and see what would happen. I'm gonna spin the chair slow and then fast. I would start in the in and move outward, going slow, and I would start in the inside and move outward going quickly, and then I would do that starting on the outside of the paper, moving inward, slow spin, and starting on the outside of the paper, moving inward, a quick spin. And I'm going to show you what that looks like, the results. It's very difficult to do, so I did it in advance, and I'm going to give you just a look at what it looks like. Okay, I went ahead and did the spins for you and drew on the pieces of paper. From the inside going outward slow, you get this little curve here. From the outside in going slow, you get another little small curve. If you spin the chair fast and put the pen in the center and go outward, what you actually find is that you draw a swirl. So the faster you have a spin, the more swirl you have. And then again, outward in, swirling very fast. And in fact, if you spin fast enough, you're going to create bands. So you can copy each of these into the spaces here in the table. And it says to describe the differences in swirl tightness. Obviously, the slower speed, it's not a tight swirl. And the faster speed is a tight swirl. And then it shows you 3 planets, Venus, Earth, and Jupiter, and the cloud patterns of each. And you see this gentle curve here on Venus. If it's got a gentle curve, what kind of speed is it swirling? Or excuse me, yeah, what kind of speed is it rotating? Not very fast, right? In Earth, you see a curve with a swirl like this, these big swooping curves with swirls in them. So Earth's moving a little faster. And Jupiter, you can't really see it maybe from the camera angle, but Jupiter is swirling so fast that there are little swirls, and the swirls make up little bands. And of course, this big swirl right here, the great red spot of Jupiter, is another example of one of those swirls. Jupiter is rotating really fast. Jupiter rotates about once every 10 hours, and that's really fast for a big boy. So Jupiter, again, is going to give us those tight swirls, so tight that they form into bands. So I ask you to categorize these from slow spin to fastest spin based on fastest spin with the number 1 to the slowest spin with the number 3 based on the curvature of the clouds and the atmospheric patterns. And obviously Jupiter spins the fastest, then Earth is number 2, and the slowest spinning number 3 would be Venus. So that's this part of the Coriolis effect. All right, part 5 also deals with the Coriolis effect on Earth particularly, and it looks at how the Coriolis effect operates in opposite directions in the northern and southern hemispheres. And we can observe this with a demonstration. I have an object here, a pen cap on a string, and what I'm going to do is I'm going to spin this around and look at how it looks from the top versus the bottom. Now, if you're spinning it here from the top, it has a clockwise spin. If you were to view the same spin from the same direction on the bottom, it would be counterclockwise. So our northern hemisphere is clockwise spin, our southern hemisphere is counterclockwise spin when it comes to the Coriolis effect. And that basically answers the questions for you there in 1, 2, and 3. All right, part 6 deals with magnetic fields. And magnetic fields are generated by planets because of liquid metallic interiors rapidly rotating. So the Earth has a liquid metallic outer core, and that outer core rapidly rotates due to the Earth's rotation. And so the Earth then generates a magnetic field. Anywhere we have liquid metal rotating quickly, we have a magnetic field. Remember how I said Jupiter rotates once every 10 hours? Well, it has a gigantic layer of liquid metallic hydrogen, one of these amazing superstates of matter where the hydrogen atoms are compacted so closely they behave like a metal. And so Jupiter produces an enormous magnetic field. To get an idea of how magnetic fields span out into space, they actually curve out away from a planet into space and generate magnetic field lines around the planet. When the sun's solar charged particles, the solar wind particles, come and hit that magnetic field, they get excited. They actually travel down the magnetic field lines, excite atmospheric molecules, and when those atmospheric molecules relax back down, the electrons release a color. And that's what actually causes the beautiful auroras. Auroras then are caused by solar wind particles traveling down magnetic field lines, hitting the atmospheric molecules, exciting their electrons, and then when those electrons relax back down, they release a color. So I'm going to demonstrate how a magnetic field operates today with this. For part 6, then, I have a bar magnet, and I've got a little plastic sheet that's going over the top of the bar magnet. And I do that so the magnet doesn't get the iron filings. I've got a container of iron filings here, and it's like an salt shaker here. So I'm going to go ahead and sprinkle some iron filings out for our demonstration purposes. Try to keep it on the plastic sheet here. Okay, and when I distribute out these iron filings in a random shape, they kind of disperse out everywhere. Okay, but when I actually let the magnet, and this is a bar magnet with the north of the bar magnet there, when I actually tap the plastic sheet, a fascinating thing happens. The iron filings line up with the magnetic field of the bar magnet. And so you can see that they're falling into the magnet, but they also have this curved shape. They have a curved shape around the magnet. And so I'm going to kind of disperse out these iron filings, and let's try that again. Okay. When the iron filings are kind of randomly dispersed and we put it on the magnet, first of all, the magnet sucks them in. And second of all, when we tap the plastic sheet, notice how the iron filings line up with the magnetic field of that magnet. Very much so like that does a magnetic field happen around the Earth. Its liquid outer core spinning rapidly with the Earth's rotation causes a magnetic field to be generated, and it extends way out into space. So when you do this with a bar magnet and tap the plastic sheet above, you can see that if I'm going to draw this, I'm going to draw a bar magnet with curving magnetic field lines. They actually exit out the north and come back into the south, like so. Okay, and so you're going to draw what you see here for part 6 under number 1 in magnetic fields. Okay, part 7, planetary interiors. What we're really looking at in this part is the magnetic field of an object, planetary object. And so the Earth, as I talked about, has a liquid outer core made of iron and nickel. And of course, the Earth takes 24 hours to rotate around one complete time. I also explained how Jupiter rotates once every 10 hours, which is pretty quickly. And it has a liquid metallic hydrogen layer. All right, that's, again, one of those extreme forms of nature, kind of an exciting thing where pictured here you have hydrogen gas where the molecules would be a little bit more spread out. Hydrogen liquid, the molecules are a little bit closer together, but liquid metallic hydrogen, where the molecules are so close together that the electrons can flow Let's try that again. The electrons can flow freely through the material. And so you get this metal sort of effect. And when you have Jupiter in its deeper layers, there's a lot of overlying pressure of all the weight of the molecules and gravity pushing them down. When you get in the deeper layers of that liquid hydrogen in Jupiter, it's liquid metallic hydrogen. Pretty amazing. And that pressure producing liquid metallic hydrogen also makes it responsible for the big magnetic field, the powerful magnetic field around Jupiter. And so this part is really exploring what would it be like to have planet X, okay? And planet X either be made of a material A or material B. And so what I'm going to do is I'm going to spin material A, and material A is liquidy inside, okay? So you would imagine that liquid interior layer. And planetary object B is solid inside. So my questions would be I'm going to spin each of these cans, and we're going to see how many rotations they make with the same sort of spin on them. And of course, the difference is going to be that one is liquid inside and one is solid inside. We'll see which one spins faster or more times, I guess. And if the cans above represented the interior of planets, which one would produce a magnetic field, A or B? And really, as we're discussing this, we realize that can A probably, because it's liquid, would produce that magnetic field. But let's just do it anyway. Let me show you how it turns out here. So let's spin can A, and we'll see the number of spins. And I'm going to slow this part of the video down so you can see We'll do a little slow-mo situation here. Ready? Okay, can A is facing this direction. Try that one more time. Okay. The same amount of spin now applied to can B. Whoa. Let's try that again. Okay, so obviously can B is having an easier time spinning around more time, so maybe that speed of spin is not slowed down so much with can B. Can A might produce a planet, cause a planet to wobble as the Earth does on its axis as it rotates. But can A also has that liquid inside, which has a potential to make that liquid metallic interior rapidly rotating to produce a magnetic field. So which would produce a better magnetic field? The liquid one. All right, and so that's part 7. All right, everyone. Well, thanks for joining me for the lab today. We learned a lot about planetary properties and how planets we can determine things like size and distance using angular diameter. We looked at terrestrial versus Jovian, how atmospheres move molecules through and temperature is really a measure of molecular motion of those molecules. We also looked at the Coriolis effect and the swirl of air due to the planet's rotation, noting that the Earth really rotates pretty rapidly, once every 24 hours, Jupiter even faster at once every 10 hours. And we looked at how magnetic fields are generated, and that would be through liquid metallic interior and rapid rotation. And we saw how a magnetic field came out of the bar magnet to show us what that's all about. So thanks for joining me this week. I look forward to seeing you next time, and hope you have a great week. Don't hesitate to email me with any questions, and I look forward to talking to you guys soon.